underway. So welcome everyone to today's HILT webinar, in which we're going to be discussing the pathways that are emerging as being among the most prospective for decarbonising alumina production. My name is Jordan Parham. I'm Strategic Initiatives and Partnerships Director, and I'm going to be chairing today's webinar while we're in a transition phase with about to appoint a new CEO. So today's webinar is a public one. So for those of us who aren't familiar with us, HILT CRC, or the Heavy Industry Low Carbon Transition Cooperative Research Centre, is a collaborative venture that brings together industries, researchers and government organisations to decarbonise heavy industry so it cannot just survive but thrive in a carbon neutral world. We have 51 industry and research partners on board from Australia and around the world who are focused on developing, demonstrating and de-risking technology to transition the iron ore and steel, alumina and cement industries to reduce their CO2 emissions. Today's webinar will be presented by Professor Gus Nathan and Dr Woei Saw. Many of you will be familiar with them, but for those who don't, just briefly, Gus is a Professor in Mechanical Engineering at the University of Adelaide and is Director of the Centre for Energy Technology, also at university. He was the bid leader for and is now the Research Director of HILT CRC, and he's also just returned back from 2 weeks in Europe, hopefully with the latest news on work that's underway there around alumina research and development. Dr Woei Saw is HILT CRC Senior Lecturer in the School of Chemical Engineering at the University of Adelaide. He's developed a patent on net zero steam alumina calcination and is leading a HILT CRC project to perform a preliminary assessment of technical and economic feasibility of low carbon alumina calcination by electrification or a hydrogen pathway. So today's format will be a presentation from Gus and then from Saw. After that, we'll have a panel discussion followed by questions and answers. So feel free during the course of the presentation to enter any questions that you have into the chat function, and then we'll get to them towards the end. Before we get into the presentations, just a couple of HILT news items for those joining us. The deadline for HILT proposals into the netting system is this Friday, 5th of May. And as even though today's focus is alumina, and many of you may be aware that there's an ARENA research and development round open in iron, steel and hydrogen that's underway, and HILT is helping to facilitate and support proposals. So if any partners are interested in that, please contact me directly for any further information. And finally, our next webinar, which will just be a HILT only event on Wednesday, the 10th of May, will be focused on HILT's Program 3, Quick Start projects, and wrapping up outputs from them and providing a springboard for future proposals. So with that, that's enough from me. I'll hand over now to Gus to take us through the exciting stuff that's happening around alumina decarbonisation pathways. Gus.
Thank you, Jordan, and thank you all for dialing in. Firstly, I'd just like to acknowledge that here in Adelaide, we're meeting on the lands of the Kaurna people and also celebrate their leaders past, present and emerging. And also to acknowledge the team that's contributing to the work that Saw and I will present. Briefly, Liok, Philip and Mujahid in particular have been doing some of the system modelling. Siyun, Suchen, Zamung and Eleanor have also been doing some of the alumina calcination in steam work. We'll present also with Philip. Alfonso and Sun, Zhao, Daniel, they've been doing some of the work we're going to present side of it, as well as Peter's contributed, of course, to most aspects, also with senior input. And I hope I haven't forgotten anything, but of course there are others in the team who also contribute. So we're going to talk about pathways to low carbon alumina. Importantly, like to also acknowledge those in our HILT, the industry partners, core partners, key partners who are mainly providing technology, the affiliate partners, associate partners, and all of the various research partners here who also contribute. So firstly, on the drivers to decarbonise the alumina process, and this is a photograph of one of the partners, who also some of the work that we present from a predecessing marina project gives you an idea of the scale of these plants. They're very large, and alumina is a vital commodity to Australia, and of course aluminium is a critical element, critical material within the Australian and the global economy. In Australia, it's also the biggest single energy consumer. It's our biggest value add export. In other words, not rather than just the ore, we value add it to a high value material. It's also very relevant to the other high temperature processes in decarbonising, because it operates, the high temperature process runs at around 1,000 degrees, but it also uses steam at temperatures of between 250 and 300 typically, which is relevant to other large processes, including petrochem, pulp and paper. And so the pathway to decarbonise this process is widely relevant to other industrial processes. It also is a significant water consumer, and 2 tonnes of water per tonne of alumina. Now, there's a lot of work being done in the industry to recycle that material, which means it's improving, but nevertheless, it's a significant local consumer of water. And so one of our opportunities and challenges is to find how we can even further reduce the water consumption by better recycling. Of course, if we're going to be using hydrogen, and some of our industry is considering that, one of the options is via electrolysis. And if that was to be employed, we'd also need water for that. So it also further induces the requirement or the target to lower water consumption further. There are a number of opportunities in this industry to look at ways to to increase circularity, to both value add and get more total products from our processing pathways, as well as to increase the sustainability of the process. Most most mining around Australia and around the world, there's a lot of clays, and clays may be in the overburden. They may be part of the mining process, and clays, hence, if they're being mined anyway, becomes also an opportunity potentially as a feedstock into some of the alternative cementitious materials. So that's another thing that we want to be looking at in the HILT CRC, is ways to use clays as part of the alternative or supplement to the conventional cement product. That's an opportunity, a challenge. Clays are recognised as being a way of substituting roughly half of the material that's used in concrete. However, we don't have very good understanding of how to process them in our plants. There's a project on that, so that's a part of our circularity we're interested in. And also in the alumina process, red mud is one of currently a byproduct, but potentially is a co-product. And so that's another thing that the industry is interested in, the decarbonising. We won't talk about them very much in this particular presentation. We'll talk more about the other elements, but they are also important and ones that HILT is working on. But today we will talk about the recovery of steam through the water, which is chemically bound within the alumina processing pathway. And that is also one of the opportunities for lowering CO2 and improving efficiency, which we'll talk about in this talk in particular. So firstly, this is a historical record showing how the energy consumption over time of alumina processing has increased very significantly, and current plants are doing very much better than the earlier stage ones. Nevertheless, there still is opportunity to further increase efficiency, and we'll talk about how, as we go shifting to the low carbon pathways, we can potentially, one of the ways of lowering the cost of that is if we can also do our processing better to save energy and hence save cost. So the remaining losses include some of this steam, which I've mentioned, the opportunity for water recovery, which is vented currently with the exhaust gases, and hence that's one of our targets. But of course, each of these losses are plant specifics, and there are a number of things that are challenging because currently they're mixed with the combustion and the products of the combustion. So we want to find ways to overcome that and gain some economics while we're also addressing the opportunities that still remain in circularity. So this is an example of where the steam comes from that we would like to recover and also save energy. So generally in the process of making alumina from bauxite, there's a series of processes which we lump into digesters. This is effectively where the bauxite comes in with impurities, and it's kind of manufactured into the trihydrate as we do this processing, and that needs steam. And depending on the bauxite, then the temperature will vary, but it's that range of 250 odd degrees Celsius. And currently this steam comes from burning fuel and air and making steam, putting it through a combined heat and power plant, which is pretty efficient compared to the earlier ways. But then that steam is then currently vented at the outlet of that process. Then the bauxite comes through and is made into the alumina trihydrate after removing the impurities. And this alumina trihydrate is heated in this high temperature reactor, and the OH is driven off as water, which is also vented. But of course, when we burn this fuel with air, it also puts nitrogen into that stream, and likewise in this end up here. And this nitrogen makes it challenging in this current process to recover this steam. So one opportunity is, well, if we're going to do our processing in a different way, where we maybe don't burn fuel and air together, maybe we can recover this steam, and rather than venting it, we can bring it back into our digestion process. And importantly, in addition to saving water as a circular economy element, this steam is in the gas phase, and it takes a lot of energy to make steam from water. That's a lot of the energy that comes in here. So we can potentially recover both water and energy if it was possible to recover that steam. And that's what we're going to talk about, because if we're going to replace the fossil fuel and air combustion together, that may open this opportunity. And this just shows the reaction where the alumina trihydrate is heated to make the alumina oxide, which goes into the electric arc furnace in the stage of making aluminium and the water. But this is an endothermic process that requires energy, which is why the heat is needed in this process. So there are different ways to potentially recover this steam. Currently, we use methane burning with air and the alumina. This means that the CO2 is mixed with the CO2 and nitrogen mixed with the steam, which makes it harder to recover, although we make the alumina trihydrate. So one option would be if we were to burn hydrogen and oxygen. We don't have any nitrogen in this system now. We've only got hydrogen and oxygen, which make steam as well. So then some of that steam, we now only have steam in this product, which can potentially be recovered. Some of that may be cycled back to help to transport the media if that was to be useful. And another way to do it is potentially through electricity and or solar thermal, which also don't have any nitrogen in the product. So then again, we only would have the steam from this alumina trihydrate, and that is one of our targets. So either of those options can be ways of saving energy and recovering the steam. But of course, each of these bring opportunity and challenges. If we directly burn hydrogen and oxygen together, it's changes to the plant. But we have the challenge is that the cost of hydrogen is significant, is currently high, and also we still have got a fair few changes to make the plant. The other, if we use indirect heating via electricity, then we need a different type of reactor. The technology is an earlier stage of development, and we still have some cost and variability in the electricity direct heating source. Solar thermal is similar, but it's at an even earlier technology readiness level. If we do the calcination in steam, which is what we see here, where the steam is recycled back, then that potentially is greater efficiency to recover the energy. But previously, how that would work in a plant, we don't really, quality hasn't been on previously. So we've been doing some work on that will show you. Saw will give that details. And if we can recover the steam, this gives us the opportunity to recover efficiency. But there's still challenges of how the particles in the steam will work. And then any non-condensable gases that come out with the steam, it's not pure steam, although it's shown here as being water, there could still be a small amount of impurities. And then it's also possible to hybridize these two together. So generally, some of the range of evaluations that we've been looking at that we'll talk about are to support changing the way in which the alumina processing is done, to do the processing in steam. We want to understand how that works to de-risk this possibility, and including the economic viability we'll talk about as well. So firstly, we've been looking at some of the alternative energy sources, be it electrification, hydrogen or solar thermal, using techno-economics, etc. And we'll show you some of those. There's a fair bit of work already undertaken. Then we've looked at what happens to the reactor if we change from doing the calcination in combustion products to doing it in steam. And we're looking at ways to recover the steam, to develop the reactor to operate in this new environment, and then how the steam is recovered, and if you've got particles in this process, how they're going to be removed. So some of this work we've done some work on, and others will be continued through our HILT CRC program. So a bit more detail about what this calcination process looks like. This is a simplified version of the calcination process. What happens is the gibbsite comes in, which is what comes out from the digestion process, and this is first of all heated in reactors that take the hot air from the combustion gases that heat this material before it goes into the furnace, so to recover some energy. This then goes into the main furnace, where it's heated with natural gas and of course air as well. And then the hot gases from that, also the material goes into a holding vessel to give it the right recovery. But the hot gases through these processes go back to here. But on the other hand, once it's been calcined, the alumina, which is the hot material, then goes into the coolers, which recover some of that heat by preheating combustion air. And this is further heated with fuel. So currently you've got this process of heat exchangers at the front and the back. You've got a furnace, and then currently the fuel is natural gas. So obviously, potentially we'd like to replace this. But there's two ways of doing it. One, we try and start with the furnace system we've already got, and we try and keep the system without having to change it, which lowers the risk. So we still keep all these heaters running. We still use air as our transporting gas to transport the particles, but we want to replace some of the energy to heat the air with replacing the natural gas. So that becomes a way of doing that. Then we want to try and do it in steam, and I'll talk about those two steps later. But firstly, we're going to look at some of the types of electrification methods that are available or emerging. So you've got thermal plasmas, which are kind of emerging, as you've got air torches, which are also emerging as replacing flames. You've got ways of potentially heating a furnace through the wall, and one of our partners, Calix, is developing a way of doing that in this kind of reactor. There's also ways of potentially using infrared electrical heating. These are different routes, and you can see that each of these are at different levels have different temperatures, different technology readiness levels, and applicability directly need further development. So, for example, heating the air resistively is commercially available as a resistive heating, but hasn't yet been applied in alumina. It needs to have clean air, and we couldn't directly put it into a process where a particle's there, but we could still use it to do part of that heating process. But the efficiency drops. It's limited to about 1400 degrees. We need to understand energy that could be implemented. And likewise, these different ways, you see they each have got different technology readiness level. They're not yet by and large ready to put into an alumina process, so we need to evaluate how they could go and look at what is 20 years. We want to be demonstrating and de-risk them further. So to the minimal change route is to change the air heating stage. Just going back up, you say currently we put natural gas into this first stage of heating. So if we replace that with electricity, such as an air heater, this could be done with technology that's available today, or potentially putting solar thermal to heat the air, which is not quite as ready, but we'll show you those options. We still need supplementary fuel to keep this furnace running in a retrofit. Longer term, we would go to this potentially kind of option where we would potentially run the whole thing in steam. So rather than running air through this process, we now run steam through the process. And you see that now potentially an alternative energy, hydrogen or oxygen, is used, and green electricity in this heating. And instead of circulating air, we're circulating steam through this process. That means steam comes out of the end, and some of this can go to the digesters rather than being vented, as we showed in our earlier diagram, and some of it gets recycled back to run through this process. So what we're going to do is show you some of the analysis and the research we're doing to de-risk this pathway, which in the long run will be potentially the most economic way, but also in the intermediate step, we can still run with air as this media, which is a step one in the process. So briefly, we've done a whole lot of techno-economic analysis of these different options, and then we'll show you some results of our calcination work, etc. Shortly. So we'll present that. But firstly, some of the economic analysis of how this could be done. I'm not going to go through these numbers in detail, but those of you who are familiar with these will be able to note the numbers on the screen. But for example, we're assuming some of the typical efficiency of these electrical heaters, assuming resistive heating. You see the capex and opex rate, discount rate of %, for example. These are some of the key numbers in this, and we've got these costs from commercial suppliers by and large, and or industry partners for the economics. So briefly, where this comes, this is we estimate the economic ability of doing this case. The electricity is provided in what we can do today in heating that airstream after process with our model. And this is the estimated parity cost. And you'll see that the parity cost in dollars per megawatt hour, this is the optimistic scenario, green power, based on a Garno study in 2030 costs. The upper rate of this corresponds to around about current average price in the Australian grid, and this would be an optimistic price down the track. And what you see is in US prices of dollars per gigajoule. So $10 US a gigajoule is around about probably 13 to 15 Australian dollars a gigajoule. And you see that if we were to have that with no carbon price, that the estimated what we'd need for a gas price to break even is about $14 a gigajoule on today's prices, which would be around about early 20 to 25 Australian dollars, which is more expensive than our current cost. So that means you would need to have something else, such as a carbon tax or maybe a higher value premium, to start to bring it into the range where it could be economic with today's prices. We'll show you then later. Saul will present the results on what happens with steam, and these costs come down to be more economic if we can recover some of the energy in the steam. So what it tells us is a simple retrofit with electrification would not yet be economic in today's market. We need something else, such as a carbon tax or a premium, to make that viable. But of course, in addition to the challenge of the average cost of electricity, we know that there's also the volatility in our prices. And this is some results from the recent inquiry into the electricity market, showing that the cost of hedging contracts is going up. Now, maybe, who knows, we don't quite know what's going to happen into the very long term, but these are the challenges, which would mean that if we're going to, as an industry, we want to be able to have ways to manage this volatility or the fluctuations in prices. So this is the kind of the options are to these kind of hedging routes, or we could look at some energy storage to try and help to buffer those costs and allow us to get more attractive costing. To look at turn down, which is currently expensive, although I know that we've got 2 HILT projects on these topics. And also another way is to try and hybridize. So this would mean when the costs are low, you buy electricity, and when the costs are high, you bring in another energy source, such as maybe hydrogen or another fuel. And so we want to look at all these options. And I guess in the industry, where we want to get to is to have a platform that allows the industry to be shielded from these high fluctuations in prices. So there are other routes than the electrification which can play a role, and these include things like solar thermal and also alternative forms of hydrogen. Photocatalysis is one of the areas that Professor Gus Nathan is working on, and this is some of Cyro's work in solar thermal, for example. And each of these are also emerging as with different costs and scale, which we don't quite know, but we think prospectively these other routes could also be prospective as we move forward. So we want to make sure that the technology we develop leaves open to these other routes, which may be part of balancing the variability in the electricity costs. A couple of words about some of the emerging hydrogen routes. We're probably all aware of the green route of potentially making hydrogen from variable electricity, and this is obviously going to be an important contributor because it's being there's increasing amounts of this being built and costs are coming down. Nevertheless, if you're going to make hydrogen from electricity, the average cost of hydrogen will be higher than electricity, although it may be cost for some amounts of it can be lower cost because you're balancing the variability. But there are other routes emerging. This is one of them, a pyrolysis route, which is different to the steam methane reforming. Steam methane reforming you probably heard of, but it generates CO2. Pyrolysis route takes methane and cracks it into solid carbon and hydrogen, and potentially carbon type products can be another valuable co-product, which can be things like replacing potentially plastics, tires, or even in the longer run, things like construction materials or carbon fibers. So this route has been estimated to have potential to go to low cost. The technology is not yet commercial, but you see now there's a commercial scale demonstrator in the US. So these are the kind of routes, and potentially because it could be run continuously, you may avoid some of the need or reduce the need for storage. There's other types of pyrolysis technology, such as one we're working on also at the University of Adelaide with University of Queensland and the Future Fuels CRC. So I guess the point is, as we think about our industry transforming, we need to be aware of these other emerging routes, which are prospective to have lower costs or contribute to a lower cost solution. So these are some of the projected costs for things like hydrogen via or CCUS. For hydrogen via these different routes. These are the commercially available routes, including wind and PV and nuclear. And you can see that some of these are projected to reach costs of around $2 US per kilogram, which is still more than double the cost of natural gas today. So some of the routes that I've met, which potentially could lower this cost further, they're not available today, but they're on the cards that may potentially do that. But we need to be aware that there are these other routes coming and designed to allow the industry to take advantage of them as and when, if they do come through. I'm going to briefly a snapshot of an example of these economics emerging for the solar thermal case, and this is some analysis that we did. I'll show you the other partners shortly, where we also looked at the potential for bringing in hot air in that same part of the process that I mentioned earlier, where we did the electrical analysis. And the idea is you would have a high temperature solar receiver with thermal storage, and then this would be piped, hot air would be sent to the plant, taken back for reheating, and you have a combustion backup system. So this is not yet commercially available technology. It's pre-commercial, but we want to estimate the potential for it to contribute in the 2030 to 40 time horizon, for example. So this system, we modelled air heating in a retrofit with a emerging type of solar receiver, packed bed storage. We modelled this full system in detail that I'll just summarise briefly with a backup. And the system was modelled as a transient model in 15-minute time steps for a year to fully account, or reasonably account, for the variability in the process. So you have the idea is you have your solar field that concentrates the energy to a receiver, makes hot air that goes through a storage system. This air gets sent with a backup burner, so that it gets sent in a pipe to our industrial process and then recycled. And each of these components was modelled, but the input solar resource is in a variable, accounting for the full variability of the resource. And we used a solar thermal receiver system we've been developing at the University of Adelaide with partners. I'm not going to go into this in detail, but a lot of this is pre-commercial, but we did a lot of testing and development. Some of those details illustrated here. Again, the techno-economic analysis was done with similar details than reported before that I won't go into in detail, but you're welcome to follow us up if you'd like to. And briefly, the key message is this, and we acknowledge also Hatch and Alcoa, who contributed a lot to this analysis work, together with CSIRO. And the important, each of these is a different potential system that's modelled to get a cost for a given plant or solar thermal plant configuration. And the levelized cost of heat, based on what, if we were to be built today with today's prices and a one-off design, you're talking around maybe $30 per gigajoule. However, if this was to be designed, rather than just designing for one-off, you just start to putting some learnings from multiple design processes, and also allow for further improvements in efficiency of the solar thermal with other technologies under development, you can then see potential to get with typically a 40% improvement in each of those. You then are talking dollars of around between 10 and 15 US dollars a gigajoule, which is in the range where other net zero heating options are projected to be as well. So this is not available yet, but they're the kind of things that could be emerging within the time horizon of 2030 to 2040, which is where we want to be designing, also considering. So not saying this is the only answer, but saying in our design process, we need to make sure we allow for not just electrification, but hydrogen and also solar thermal, because potentially they could all play a role. So I'll summarise where we're up to date, then hand over to Saw to tell you about some of the more details of the calcination in steam work that we've been doing. But firstly, we think that steam recovery from the calcination process is desirable. It offers potential to increase efficiency and circularity of the alumina production process. Also, steam recovery would be synergistic with some of these emerging alternative energy sources, because you wouldn't be diluting the steam that comes in the process with nitrogen and CO2. So electrification and hydrogen and solar thermal are all potentially synergistic with that, and are potentially economically viable, although technology development would be needed to enable them to occur. But of course, there's currently, where we sit, there's significant uncertainty in the projected costs and heat transfer characteristics of each, which is why we need to better understand them and de-risk them. And also, we don't know any of these emerging platforms that I mentioned. There could be breakthroughs in alternative ways of making hydrogen or solar thermal or electrification, which may make any of those prospectively more desirable, but also electricity is variable, so having hybrid options is desirable. So in the technology we want to develop, we want to retain flexibility to allow the industry to utilise a range of sources, and hence we want to de-risk their viability. This means we need to have things that could be implemented today as step one, but also to achieve all these things and make it more economic, we need new technology development to increase both the efficiency and the circularity. And I'm going to hand over to Saw to now talk you through that. I've just got to find where I'm going to stop my sharing. Where are we? Come back to here. Over to you, Saw.
Thanks, Gus. Let me quickly grab my slide. Can you see my slide, Gus?
Yep, we can see it.
All right. I guess thanks, Gus, for that introduction in terms of like how we can kind of get into this low carbon alumina calcination pathway. So what I'm going to talk about it over the next 10-11 minutes is basically focusing a lot on the research, more onto the fundamental work that we have done. So just going back to a bit of like chemistry, what this alumina calcination reaction pathways look like. So based on the literature review that we have done, so there are many different pathways, as you can see, depending on the types of reactors, the conditions. So as Gus mentioned earlier on, so basically the raw material to produce alumina is the gibbsite, which is you can see from the top left-hand side of the diagram. So obviously, it depends on which pathway, as I kind of mentioned. So what we have looked at predominantly the pathway that's kind of like happening in the existing industrial calcination is kind of like in the way of like gibbsite, bromide, gamma, delta, and theta, then alpha. So these are the kind of like predominantly pathways for this alumina calcination. So obviously in this case, for the alumina quality or in terms of the type of the alumina that's required for the SGA is predominantly sitting in the gamma. So this is what the kind of specification that we've been kind of like having this sort of discussion with the industry partners. And obviously you don't want alpha because of the low surface area. So obviously low Li, but unfortunately the surface area is too low for the smeltering of the alumina into aluminium. So all right, so before we go into that, so I think you heard about the previous part of the discussion is more to steam calcination. So what actually happened in terms of the kinetics of the alumina calcination inside the reactor? So obviously, it's not going to be a kind of straightforward to kind of test, put steam into the actual calciner to try to understand what's happening. So therefore, what we're trying to do is to kind of do a kind of like preliminary stage to understand what actually has happened to the phase of the alumina for different conditions, especially temperature, residence time, and also the steam concentration. So we have literally have this particular system, as you can see, is a horizontal tube furnace where we can control the temperature, as you can see here, and then of course at the same time we can control the steam environment. So we are varying from 0, which is literally using nitrogen, and then up to 50%, 50%, then up to 80%. So typically 50% is around the kind of like current steam concentration in the calciner. So obviously is around, depending on the system, so it could be ranging from 40 to 50%. So here what actually we have done here is that literally once we so here we set up the furnace temperature to, let's say, 600 degrees, 700 degrees. So once it's reached the temperature, then only we are sliding the sample of gibbsite into this reaction zone. So when we finish, like for example, hold it for a couple of minutes, like 10, 20, 30, so you probably will see the result shortly. Then we will pull it and then cool it down to in the cooling zone before we take out the sample to do the measurements of the weight. And then as you can see, and then after that, we're going to look at the loss of ignition through TGA. And then we have analyzed the surface area of the sample, the pore size distribution, also the crystal structure using XRD. So I'll explain a bit more shortly. So this is one of the examples. So what we have done is literally we put a gibbsite sample in there, and then we heat it up to here 600 degrees, and then we hold it for 10 minutes. And then we did another series. So obviously you got 80% steam, 50% and 0% steam. And then we look at different temperature and then also residence time. So this is the graph or the results that we got here. Literally is the surface area as a function of LI. And we have a kind of reference case. So basically, this is the kind of specification that we need to try to achieve, or this is the target for SGA grade. So typically, it's like less than 1% LI with about roughly 70 meters square per gram. So we have looked at a number of cases here. So especially if you're looking at 650, so as you can see here that we cannot understand that because of the low temperature. So obviously you're going to have a relatively high LI and also high surface area. But as you hold it from 10 minutes to 30 minutes, you can see that the LIs kind of drop from literally from 1.7 to 1.2. But then as you increase the temperature here from 650 to 750, you can see that there's a significant reduction in terms of the LI, but not so much on the surface area. As you can see, we are still typically around 100 meters square per gram. And then as you really ramp it up the temperature to 850, you can see that the LI is literally less than what the SGA and also higher surface area. So obviously there's quite a bit of benefit of doing this, especially on the other side, when you're producing the aluminium. So obviously I'm not going to go into details. So this is kind of our first step to kind of understand what's happening to the sample. But of course, this is the kind of some of the things that we have identified in terms of the pore size distribution, because when we are measuring the surface area, you get this sort of information, and also looking at the SEM, try to understand, in terms of the cracks and this sort of like structure. So unfortunately, I don't have enough time, so probably I'll move on. So certainly, I'm happy to discuss a bit further. So once we kind of done through, literally we are jumping from gibbsite all the way to gamma, delta-ish. So what actually has happened between, gibbsite, boehmite, or boehmite to gamma? So that's why we have a program literally done by Zichuan. So literally it's trying to understand what is the transformation from gibbsite to boehmite as a function of temperature, residence time, and steam concentration. So we have done quite a bit of series of studies to try to understand, and we are using different types of methods. One based on weight loss, as you can see figure on the left-hand side. One looking at the literally analyzing the crystal of the boehmite using XRD. So we have done this through quantitative XRD measurement so that we can understand what's the boehmite concentration. Whereas on the left-hand side, basically we are assuming that the weight loss is representing how much gibbsite is converted to boehmite. So what we have found that if you look at these two figures closely, ideally it should be having the same sort of numbers, because this is what we are expecting. But interestingly, what we have identified here is especially looking at this particular two dots here, is that in fact, even though we don't see any weight loss in the first 5 to 10 minutes, but when we look at the XRD, we found that there's quite a bit of gibbsite already converted to boehmite. I mean, this is what you're talking about around about 250 degrees. So it's relatively low, because we really need to kind of slow down the reaction so that we can kind of study the kinetics. So this is one of the things that we have discovered, that in fact, what we found out there's a kind of boehmite intermediate between the gibbsite and boehmite. So that's what we have identified. Sorry, I just muted myself accidentally. So what we have done next is literally from boehmite to gamma, we have done the same thing, is try to understand what actually happened to those phases as well. So similarly, things that we have identified that like there's a kind of intermediate stage between those stages, which is not found in the previous literature. So this is kind of an interesting finding from what we have done over the last year or two. I mean, basically what we're trying to do is to understand the kinetics, but somehow during the process, we kind of unlock a number of things that yet to be kind of reported in the literature. So therefore, that's why we have prepared a couple journal articles that to be submitted, what we have achieved. And then, so obviously these are the reaction constant. Once we got those information, we will convert that. Basically, what we are going to do next is basically you will see. Before I go into that, so basically what I'm trying to summarize in this is basically we have identified a number of intermediate steps between gibbsite and boehmite, and also from boehmite to gamma. So we still got quite a number of things that we are yet to be kind of finalized, but this is something that we are going to present, or we're going to publish it relatively soon. So in terms of the kinetic data that we collected from those experimental work that you have seen, so, and then also we have found some kinetic data from the literature. So what actually we are trying to do is to put that into our model. So this is one of the ways that, because when we are looking at sort of like hydrogen pathway or electrification pathway, you need to understand how this kinetics will kind of like influence the reactions of the gibbsite to boehmite. So I mean, obviously steam in this case, what we have found out is not something that is not going to be a kind of like catalyst, but obviously there will be some inhibition in terms of steam, especially at lower temperature. But at high temperature, it's kind of tends to fasten the reactions, as you might see in some of the stuff. Unfortunately, I didn't have the time, but definitely there will be some sort of, you know, inhibitors from the steam, and also there's a promotion of the steam for this calcination. So quickly, just what kind of Gus mentioned, you know, literally this is just a kind of a slightly a bit more information about how you do this hydrogen pathway, how you do this electrification pathway. So what we have done is like we have modeled those two based on some of the information that we gather from the kinetics data, put into the process model, and we are trying to model different pathway in order to understand what is the energy consumption. So overall what we have done here is like, again, we have done through this using Aspen model. So obviously we are fitting into those kinetic data into the main furnace, the reactor, and also the one of the cyclones in order to understand how that will influence the reaction time, energy consumption. But this is what you can see here, that the overall energy consumption for the natural gas is between 2.8 to 2.9, whereas for hydrogen is quite close. You know, roughly between 3 to 3.1. And then for electrification is between 85 to 88 megawatt electricity. So what we have literally calculated here is basically in terms of the how much steam can be recovered is about roughly 42% of what the steam will be consumed in the digestion. So when you're talking about per alumina, so this is tons of water per tons of alumina. So that's what you can see, that there's a significant amount of energy, or also steam that can be recovered. But of course, the other part of the question here is like how much energy is required to recover the steam. So again, so we got some of the information that's kind of published by our industry partners, I think Alcoa. So some of the work that they have looked at MVR. So without going into details because of the time constraints, so what actually we have done here is like we have looked at a series of different steam recovery options by combining, you know, literally MVR, TVR, and also TVR only or NVR only. So obviously I won't be able to provide a lot of the details, but just to give you a snapshot in terms of the cost per ton of steam that recovered versus what is going to cost for the conventional case or the reference case, which is using the natural gas boiler. So we have done one case for the hydrogen pathway, the other case for the electrification pathway. So obviously there will be some steam not just coming from the calciner, but there will be some steam recovered from the digester and also the evaporator. So without going into details because of the time constraint, I'd like to move on, pass it over to Gus to kind of wrap up the rest so that we have more time for the Q&A session. So Gus, hand it back to you.
Thanks, Saw. Can you just click forward to the conclusions? You stopped sharing.
Am I stopped sharing?
You did, yeah.
All right, I'll put it back. Can you see that?
Yeah, I think that's it. So conclusions, firstly, that there are significant limitations in how we could decarbonise alumina calcination with existing technology. We can make significant steps, but it's very challenging to go all the way with existing technology. Hydrogen is technically plausible, but currently expensive. Electrification, we estimate that we could do about 50% substitution with near commercial technology, but that is also currently expensive. On the other hand, emerging technologies offer significant potential both to increase efficiency, which could then offset some of this higher cost, and increasing the viability of recovering the steam, which potentially could save 15% of the energy. And the preliminary techno-economics suggest that this would get potentially close to current costs. So calcination in steam also offers potential to increase the product quality, and Saw showed the higher surface area for the same loss on ignition. And the process modelling has identified configurations, as I say, that could make this economic. But of course, further investment and technology development is needed if we're going to harness this opportunity. We need to be able to look at how to upscale the technology, confirm that the product quality that we've measured in the lab would continue to operate when we are in more realistic conditions, and identify unexpected challenges. And we need to address how to actually recover the steam in practice, which would include things like removing particles and also changing the pressure from the pressure which would be in the calciner to take it further up. So technology development is needed, but potentially looks as though this route would offer significant economic opportunity and make it relatively cost competitive. So thank you, Jordan. I'm going to hand back and
yeah, thanks, Gus and Saw, for a very comprehensive and wide-ranging presentation. I believe we have David Cochrane available, who's from South 32 and a core partner of HILT. Louise, if you're able to get David up, I think he was going to lead off with a question or some points regarding that. Perhaps maybe while that's been underway, just remind people there are. There's David.
Yep, sorry about that. Sorry, Jordan.
That's right.
Yeah, thanks, Gus, and thanks, Saw. That was very comprehensive. A short period of time that you had to cover a lot of ground there, but I think you give everyone a flavour of the extent and the depth of the work that's currently happening within the CRC and at the University of Adelaide. So thank you very much for that. I guess I'd like to just kick off with one general question to both of you, and that's the retrofit versus the greenfield dilemma that we have. I mean, obviously we have lots of installed capacity, and desired priority would be to, can we achieve a viable retrofit? It's obviously potentially easier with starting with a clean sheet of paper, but maybe you can comment on the difficulties in the retrofit area.
Yeah, I think this is a really important point, David. Obviously, we know that that if we can make use of the existing capital plant, so the preliminary analysis suggests that the electrification and solar thermal routes, you could do up to 50% in ways that keep the plant running more or less as it is. I think hydrogen would be, you could go further than that if it was cheaper, because it's more straightforward to put hydrogen in and replace the burners. The cost would be more. If potentially it may be possible to also run steam through the same process plant, and obviously or you may replace just a part of it, such as the calciner, but it still retain some of the other heat exchangers, and you would still be able to retain the bigger part of the capex and all the digesters, etc. So I guess the full analysis of how much of that would need to be replaced is what we still need to understand. But I think the concept would be to at least retain the bulk of the capital in all the digesters and upstream processing, and maybe replace the calciner, but keep some of the preheaters. But the full analysis of that is we need to work on, because obviously if you're going to run with different energy sources, there's more understanding of how that goes. But the target would be to try and make use of much of the, or to find ways to make use of much of the existing plant that's there. But it probably would be a staged process to get there.
I'll just add a few words. So I kind of agree that it's going to be a stage one, but after I've done quite a bit of work, like especially the project that we are looking at here, I think potentially there could be a kind of like a smaller calciner, especially when you're looking at just steam calcination. I think there's a benefit of this sort of new design. So that's something that we're still in the process of weighing it. But because there's number of trains of refineries, the calciner in a refinery. So obviously there will be a stage by stage. Potentially can be some of it could be do the kind of the retrofitting. There could be a couple that can be a completely new system, because this is something that we are talking about de-risking. So obviously it's going to be very expensive to have replace all the calciner, but it could be doing stage by stage. But certainly the greenfield one is going to be quite interesting, because it could be a much smaller, it could reduce the capex, because you don't need such a bigger volume like what you do in the conventional calcination plant.
Thanks, Saw. David, any further points, or otherwise there's a couple of questions coming through on the chat that we might try and address in the time available.
Okay, yeah, try and look after the chat, Jordan. Thanks.
But Saw, the first one's from Adrian. I'm not sure if you've seen that in the chat box, but I'll just read it out for everyone. So is there any reason for not considering 100% steam environment? And why for hydrogen is the gigajoules, but I mean, more than that of natural gas and Aspen plus modelling? Is it due to the choice of reactor, e.g. Gibbs, in contrast to Stoic?
Thanks Adrian for the question. So the reason why not 100% is due to the limitation of the steam generator that we are using. So obviously this is the limitation of the steam generator. So we are going to phase it out, and we would like to look at 100% steam in the next phase. In terms of why hydrogen, so it's a good question. So this is something that give me a bit of time. So it's not due to the choice of the reactor, because we are using the same sort of reactor or model for the both methods. So I'll come back to you, Adrian, given the fact, because this is something that probably I will get back to you on that question.
Okay, now there's two more questions. We are slightly over time, so maybe we'll address one of them. So we'll see if we can address both of them very quickly. First one is, can the panel comment on any materials performance issues that need to be solved from Philip? Or finally, testing calcination in a steam-rich atmosphere. Why choose nitrogen atmosphere and not the atmosphere you'd find in a refinery?
I mean, in terms of the steam, I guess we think that generally the reactor, etc., is not likely to be a problem with steam. However, there are potential, we don't yet know, issues around stickiness, etc., which might become challenges that we need to understand. There could be some stickiness. We need to make sure we avoid any potential blockages. So these are things that we really need to look at those with smaller scale systems. We look at the whole plant running. So I think they're the issues that we're anticipating more so than any like issues of refractories or the plant materials.
Yeah. So in terms of the material performance issue, so obviously this is another thing. So under steam-rich environment, what we see that because steam is kind of putting some of the pressure onto the particles, so potentially we could see that there's a less particle breakage. But also, of course, this is based on the chemical kind of like analysis. But in terms of like actually physical, it all depends on the design of the calciner. So whether you're going to have the similar like what you do like with the cyclones, with the flash type. So again, it all depends on how we're going to design the calciner and also the particle gas separation. So that could influence the erosion or the particle breakage, during that separation process. So that's something that we definitely would going to look at in the next phase. So the last question. So you're right. So literally, as I said to you, that 50% is something that we kind of like see that is very close to what you will see in the cyclone 2, which is before the main furnace in terms of the steam concentration. Whereas like we have done some 25%, but we just not put it into the system. So, and then again, 100% is not because we don't want to do it, just because of the limitation of the process. So definitely in the next phase of the system, definitely we will be able to look at the whole range of the steam environment. Thank you.
So thanks everyone. I think we are slightly over time, so we might conclude proceedings there. I think if you do have follow-up questions for Gus or Saw, please reach out to them individually to follow up. But thanks very much, Gus and Saw, for that presentation. David, thank you much for your contribution. To everyone that joined today, thank you for being part of the discussion. Please look out for future HILT public webinars that will be announced. As I mentioned before, there'll be one around the HILT Program 3 project outcomes next Wednesday afternoon. So yeah, thank you much for joining us, and look forward to continuing our journey together to decarbonise and de-risk the transition PEP industry.
Thank you all.
Thank you. Thank you, Jordan. Thank you, Gus.
Thanks, Jordan. Thanks, all.
Thank you.
Thanks, David. Bye.